Yes, I will start. Thank you for inviting me this very precious meeting in Turkey. I missed to go there, and I've been there once more 10 years ago. So then, today's my talk is on this type of MGB2 experimental study on a flux trapping and the flux jump on a PFM, pulsed field magnetization process for MGB2 trapped field magnet. So collaborators are here in Shibaro Institute of Technology, the student and the professors, and the Niigata University, and then the Lorraine University, Green in France, and the IFW Dresden, and then the Caen in France, and then the Ashikaga University. In a context, the flux trapping magnet is made of the bulk of magnesium dibride is characterized as its very beautiful conical trapped field distribution because of very nice microstructural uniformity of the material. The world record of the trapped field was reported as 1.6161 Tesla by Professor Fujishiro's team last year. But since the potential trapped field is several Tesla as reported, the performance is expected to be improved further. The most crucial drawback is frequent happen flux jumps in its PFM, pulse field magnetization operations. Then we should precisely observe the flux motion inside the bulk during PFM processes. Then the samples we made by the hot pressing and spark plasma sintering. The samples were made by Professor Hassa in IFW Dresden, and the other is provided by the Professor Nudem in Caen University in France. Today's talk, I mentioned on this to a couple of materials we discussed on a couple of the samples made by hot pressing and spark plasma sintering SPS in Dresden and Caen respectively. Hot pressed sample is a little bit thinner and lower density, including small amount of titan. So then, SPS sample is a little bit thicker, having a 9.6, so very thick sample, or very a little bit thick sample, and dense 2.6, nearly to the ideal density and pristine. This is a view graph, XRD patterns of the hot pressed samples as an sample, as for example, in features made in IFW Dresden. So the pellets mainly consist of MgB2, including MgO and Mg metal. And then the titan added to the sample from in this view graph remains pre-acted. So that is that exactly exists as a metal because of the very small amount of the addition. In experimental equipment for the PFM is shown, conducted in Ashikaga University in Japan. We employed a two-stage cryocooler cooled the bulk sample to 14 on the cold head temperature of 14, and then 17.8 Kelvin that was measured at the sample surface before the PFM operation. A Hall sensor, shown in the yellow color, a Hall sensor and a Celnox temperature sensor were attached on the sample surface. So then after the cooling to the ultimate temperature. This is the ultimate temperature without any heating or the temperature controlling. For the various pulse field with a rise time of 10 milliseconds was applied to the sample like this. So at first, we must define the parameters to estimate it. Field penetration ratio, BP over BA. This is BP over BA, and the field trapping ratio, BT over BP. BT, this one, at the last, and BP, were defined to estimate the field trapping property. BA is a peak of the field supply. That is from the shunt resistor. So the BP is the highest value of the whole sensor detected. It is a peak, corresponding to the peak. So then the BT is the final drop to field like this. BP and BP over BA indicates the shielding effect. And the BT over BP corresponds to the pinning effect. So this is the very important parameters. So these are the results of the PFM. On the MH104 means the sample from Dresden. This graph shows the applied field dependence of the penetration field BP and BT, trapped field BT, for the hot pressed sample. The magnetic flux reached the sample center at over 0.6 Tesla application. The shielding effect remained even was kept even in a higher field region, applied field region like this. After the showing the as for the BT trapped field, after showing the maximum value of 0.77 Tesla like this, flux jump frequently happened in high field over 1.3 Tesla in this sample. So these circles means show the flux jump happen. So then it is very characteristic. We don't see any flux jump in this point at the 1.4 Tesla application. So it is very interesting. So then the penetration ratio of the BP over BA and the trapped field ratio, BT over BP, is shown in this figure plots. So penetration ratio is showing a constant value over 0.6 to 6 Tesla region, with keeping slight shielding effect like this to the 100%. Trapped field ratio shows two groups like this, the higher one and the lower one, with and without flux jump occurrence. So then these are the field, the flux jump happen. So then the upper group decrease with increasing the trapped field, increasing field showing the very fast flux flow like this. We call this afterward the fast flux flow region, and the no flux flow region is detected, observed in this area. High value of over 90% without showing fast flux flow identified as no flux NFF region. So then we take just one sample, and the temperature difference between before PFM was estimated. In spite of the temperature difference of 23 Kelvin and 26 Kelvin, this is just a little difference between the sample temperatures. These are the 14 and 18 is the cold head temperature, so that is reflected like this. So in spite of the temperature difference like this, the total overview is quite similar. The highest trapping trapping field reached 0.67 Tesla, like this, in both PFM. But in a high field of over 1.4 Tesla in this field, the flux jumps degraded the trapped field as well. So there is no big differences between that. But for the region 1.2 and 1.1, in this region, shown in the blue allow, the field trapping behavior is significantly different. So sudden flux jumps lowered the trapped field, even at the same field application with slight temperature difference of 3 Kelvin. So then we want to say the reproducibility of the PFM is a little bit astonishing. So then the trapped evaluation profile must be evaluated like this at the different temperatures of 23 and 26. This is the view graph. This is the same, incidentally, same point, 0.67 Tesla was the highest trapped field performance. At the highest trapping, penetrated field remained the same value, almost the same value over 90% without any decrease like this. In this view graph, we can see very straight line, red line of this in this point. So then this suggests no heat regeneration affected the flux trapping behavior. So we call this field NFF, no flux flow region. This is very, very ideal. So we want to expand these areas. So in the second one, these are the for the areas of this 1.1 or 1.2 Tesla. At 1.2 Tesla application, trapped field decreased to the 0.5, like 0.5 is here, 0.5, due to the FFF till 50 milliseconds. This means that FFF, fast flux flow, is appeared like this way until the 50 milliseconds, and then it goes straight like this to the BT. And for 23 Kelvin, a flux jump happened at 500, very, very lately at 550 milliseconds here, and which dropped the trapped field BT to 0.112 Tesla. So it is what's a pity. It suggests the difference of the temperature is responsible for the flux jump property and occurrence. So then, when we see the just before the flux jump occurred, the trapped field remains 0.56 Tesla. That means here. So then it is very, very important to suppress the flux jump occurrence anyway. So then we must compare to the hot press and SPS plasma sintering, spark plasma sintering. The red one is the SPS, and then the black one is the hot pressed sample. The highest trapped field is similar for each other. So then the black one is like this way and goes like this way, and the red one is like this way. So a little bit thicker SPS samples show the stronger shielding effect than HP samples like this. That means the red plots of the red points shifted onto the higher side of the field application. As for SPS, flux jump happened at over 1.6 Tesla in this region. So this is quite a little bit higher field in comparison with the HP sample. One sees two groups with and without flux jump happened as well. So the total tendency is not different as well. So then we see the trapped field ratio, BT over BP of the SPS sample. So we can see the same tendency. Flux trapping ratio behave as the same as HP or the SPS, like that. The flux penetration is classified in 3 groups like this, or 2 or 3 groups, and NFF, and FFF, and FFF, and flux jump like this. So then the first flux region is here to the half of the maximum of the BP. And then the flux, no flux flow means 95%, very excellent to the of the very lower applied field region. So flux jump lowered the flux trapping to 10% over 1.6 Tesla. So then we may see the evaluation, time evaluation profiles like this on SPS sample. So at the red one is number 1 shows this, and the number 2 purple line shows the number 2 of this shot. And then the third one is green, like the shot. At NFF, no flux flow region, flux invasion was perfectly kept at 90, nearly 100%, 96%, which means no heating exists in these areas. So it is ideal. So at 1.7 Tesla, highest of the 0.75 Tesla was obtained as 53 of the BP after this fast flux flow occurrence. So then the flux jump happened at 420 milliseconds after the flux flow like this. So then it is very, very lately shown. So which degraded the BT to the 0.14 Tesla, which correspond to the only the 10% of that. So if no flux jump, when we see can suppress the flux jump, the BT should have been 0.61 Tesla like this. So then we must summarize my talk. The various flux jumps were carefully examined in a PFM experiment. The flux motions were classified in 3 categories of the NFF and FFF and flux jump regions. Very slight temperature differences caused flux jump, possibly due to the heat propagation or the low specific heat of the material. To enhance the flux trapping, we need to improve the thermal properties prior to JC values. Thank you so much for your attention.